As per Google statistics, the IPv6 adoption across the world is 40%. In other words, 40% of users access Google services via IPv6 protocol. World has essentially run out of available IPv4 addresses. You need to learn IPv6 now. Today we'll discuss a few basic concepts of IPv6, just enough to get you started. I will show you how IPv6 addresses look like, how those addresses are assigned, and how IPv6 finds neighboring devices and routers on the same network segment. My name is Philip. Let's get started. First, I will introduce you to the IPv6 address format. The IPv4 address that you are used to is represented by 4 numbers ranging from 0 to 255, separated by dots. IPv4 address is 32-bit long, that's 4 bytes. IPv6 address is written in hexadecimal format. Hexadecimal uses digits 0 through 9 and letters A to F to represent values. So, A in hex is 10 in decimal, B in hex is 11 in decimal, and so on. The reason for hex notation is that in decimal you need 3 digits to code a byte, in hex you need only 2. IPv6 address consists of 8 groups of 2 bytes written in hex notation. IPv6 address is 128-bit long, that's 16 bytes. Each group is separated by colon. The IPv6 address can be shortened, also called compressed, using several rules. First rule is you can omit leading zeros in each group. Second rule is you can replace consecutive groups of zeros with double colon, but you can do it only once. So, 0dB becomes just dB, and 0040 becomes just 40. That's the first rule, omitting leading zeros. Those consecutive zeros can be replaced with double colon. Mind that consecutive zeros can be replaced with colon only once. So for example, if we have such an address that has 2 groups of consecutive zeros, only the first group can be replaced with double colon. 0dB becomes just dB. First group of consecutive zeros can be replaced with double colon, but later we cannot replace those zeros with double colon, as we've already done that with previous group. We can only strip leading zeros, so this section becomes a 0, and this section becomes a 0. There are some predefined network ranges and addresses that you need to know. 2000::/3. This is the range of global unicast address space. In other words, that's the list of all public unicast IP addresses routable over the internet. Those addresses are globally unique, so no 2 devices should have the same address at the same time. Sometimes you'll see this route as the default gateway to the internet, as technically it covers all unicast public IP addresses. $:0, that's the default gateway, equivalent to IPv4's 0000/0. $:1, that's the loopback address, equivalent to IPv4's 127.0.0.1. FC00:7, that range is ULA, that stands for Unique Local Address. It has similar purpose as private IPs in IPv4, so 10/8, 172.16/12 or 192.168/16. It's mostly used for internal communication, as those are not globally routable on the internet. FE80:10 is a special range of addresses called link local. They are automatically generated and assigned to each interface on the system. Those addresses are used for communication within the same network segment and for neighbor discovery. We'll talk about it in a bit. Link local addresses are not forwarded outside the network segment. FFFFCF8 is dedicated to multicast. That's used for one-to-many communication. Multicast plays very important role in IPv6. There are three multicast addresses that you should know. FF01:1, this is a multicast group used for communication within all interfaces on the same host. FF02:1, this is a multicast group used for communication within all nodes within a network segment, so all devices on the same link. FF02:2, this multicast group gathers all routers on a network segment. Another difference between IPv4 and IPv6, apart from IP address length, is the way it discovers its neighbors on a LAN segment. In IPv4, whenever a device, for example node 1 that's 10.230, would like to communicate with node 2 that's 10.231, node 1 needs to find the node 2 MAC address. First, it will check its ARP cache to see if the MAC address is already there. MAC address is not there. It will then send an ARP request to a so-called broadcast address. This will cause all devices in the network segment to receive this request. In the request, node 1 is asking who has 192.168.10.231 IP, please reply to 192.168.10.230. Basically, node 1 is asking whoever has 10.231 IP, please send me your MAC address. Only the device with this particular MAC address will reply back. We do see node 2 replied with its MAC address directly to node 1. Node 1 will store the MAC address in its cache for future use. In IPv6, this process is totally different. IPv6 has very large subnets, so sending packets to all hosts on such subnets just to find the MAC address of target host would generate enormous amount of traffic. Hence, in IPv6, they did invent a brilliant thing, Network Discovery Protocol. Let me tell you how it works. If we look at node 2, that's the target we want to find the MAC address, we'll find it has an auto-generated IPv6 link local address. You will recognize the link local address as it starts with FE80. You will also find that our node did join a few multicast groups. This group targets all interfaces on this host. This group targets all devices on the link. This group is the most interesting. It consists of this prefix called the solicited node multicast prefix combined with the last 6 hexadecimal characters of the address. So, FF02:1:FF prefix together with the last 6 digits of the link local address, that is 192.551, is what makes the solicited node multicast address. I will go back to node 1, that's the source host, and try to get MAC address of node 2. We see that node 2 MAC address is not in our cache. Let's dump ICMP traffic to see how the process of obtaining the MAC address will look like. We'll use ndisk6 command that's used for neighbor discovery. You just specify the target IP and the interface. Let's analyze what just happened. Node 1 was able to figure out the multicast solicited node address by combining the FF02 multicast prefix with the last 6 digits of the target IP. Then it sent an ICMP message called neighbor solicitation to the solicited node multicast address of node 2. In that message, Node 1 asks for MAC address of Node 2, but also provided its own MAC address so the recipient knows where to reply. Because Node 2 is the sole member of that multicast group, only Node 2 got the neighbor solicitation request. This approach is far more efficient than IPv4, where all nodes get a request about who owns a particular MAC address. What happened next is that Node 2 did reply with a so-called neighbor advertisement that tells the Node 2 address and its MAC address. SLAAC indicates that this message was sent in a response to a neighbor solicitation request. OVR flag indicates that the advertisement should override any existing cache entry. Notice, both neighbor solicitation and neighbor advertisements are ICMP packages. Our neighbor discovery cache entries were updated with the MAC address of Node 2. Now we can freely communicate with the target device as we know its MAC address. Our interface has only the auto-generated link local address. Link local addresses are only valid within a single subnet or link. For our host to communicate with the internet, we'll need a global unicast address, a public IP. Mind that unlike IPv4, where your server has a private IP and is sitting behind a firewall, performing NAT to a single public IP, here in IPv6, all hosts get their own public IP. Yes, you heard correctly. Each host has their own global unicast address. There are few ways to get such address, but the most common in home networks is by mechanism called Stateless Address Auto-Configuration, or SLAAC for short. It's a mechanism that allows devices to automatically configure themselves with an IPv6 address without needing a central server like a DHCP server. Let me show you how it works. When an IPv6 device connects to a network, it first assigns itself a link local address. That's the address that starts with FE80. This address is automatically generated using the device's MAC address. Before the device starts using this address, it will first check through the neighbor solicitation if anybody else is using this address. We are past that point already as we have our link local address available. Next, the host will send a so-called router solicitation message. This message basically asks for configuration information from any routers on the network. Let's first start network capture on node 1. Then let's open the network configuration file on node 1. I did intentionally block sending router solicitation messages and accepting router advertisements message as it's enabled by default. Let's reload network configuration. Here we go. Our host did send a router solicitation message from its link local address to FF02::2. That's the multicast address that targets all routers on the link. Our node asks, hey, are there any routers out there? The router did reply with a router advertisement message. Mind that the router advertisement message was sent to FF02::1. That's the multicast address of all nodes on the link. We are part of that group. So the router did reply to every node out there. If we look at our neighbor discovery cache, we find the link local address of the router. Let's check our address on the ETH1 interface. Do you see that? We have a global unicast address, a public IP. If we look at the route table, we'll discover this 2001:470 network is accessible via ETH1 interface. Proto-array means that this route has been dynamically discovered and configured via router advertisement message. Because this public network is on ETH1 link, we can perform neighbor solicitation. We know the public IP of the router, so let's check its MAC address with the ndisk6 command. Mind that the request was sent from our link local address to the solicited node multicast address of the router's global address. Router did reply with a neighbor advertisement that contains the MAC address of the router. The reply contains a special flag indicating the host you are connecting to is a router. Another thing worth mentioning is the fact that we have a default gateway set. It points to the link local address of the router. Okay, so we have the public IP on our interface. We also have the default gateway. Let's see if we can reach an IPv6 host on the internet. Works. One question that has not been answered is how our global unicast address was assigned. Let's look a bit closer on the router advertisement message that we got as a reply to our router solicitation message sent to all routers multicast group. I will use the rdisk6 command that implements a router discovery protocol in user space, as this process is done in the kernel. To send a router discovery message, you just run rdisk and provide the interface name. Stateful address configuration. If this was set to yes, then the host would have to use DHCP to obtain their IPv6 address. In our case, it's set to no, so we don't need to use DHCP. Router lifetime. How long this message is valid? 30 minutes is the default value. How it works is that the router will send a periodic advertisements to the multicast group targeting all hosts on the network to keep their information up to date. If, however, this timer expires and a device has not received a router advertisement, it will send a router solicitation message to request a new information from the router. This technique helps to adapt to potential network changes or router failovers or restarts. Link maximum transmission unit. This is the maximum size of a packet we can send over the link. Very useful information, but not all routers advertise that. MAC address of the router. The DNS server. Devices on the network can use this information to configure their DNS settings without the need for additional configuration steps. Of course, it's also common for the DNS to be obtained via DHCP. SLAAC and DHCP can work together. Then there's the prefix, the most important information. That's the network this particular router handles. Mind that Stateless Address Auto-Configuration is specifically designed to work with a /64 prefix length. You will see the /64 prefix length a lot as it's required for address auto-configuration to work. Apart from the prefix, there's an on-link flag. It indicates that the network prefix is directly reachable on the local link, allowing hosts to communicate with each other within the same subnet without involving routers for forwarding traffic. Another important thing to look at is autonomous address configuration. If it's set to yes, usually it is, it means that the hosts on the network are allowed to automatically configure their own IPv6 addresses based on the prefix advertised by routers, without the need for manual configuration or a DHCP server. We also have information how long the prefix is valid, usually it's 30 days, and what's the prefix lifetime, usually it's 7 days. Few things to mention. IPv6 routers can advertise multiple prefixes. This allows routers to inform hosts on the network about the availability of multiple subnets or address ranges. IPv6 routers can advertise a network prefix with the on-link flag set to no. That will indicate that the network is not directly reachable on the local link. Instead, hosts need to send the traffic destined for that address within that network to the router, which will then forward the traffic to the appropriate destination network. You also need to remember that if you want to communicate with the link local address, for example, I'd like to ping the router's link local address from node 1, you need to explicitly specify the interface name. If we look at node 1's interface IPs, every interface has an FE80 address assigned, so host would need to know which interface to use. We specify the interface name after the %sign like this. The router advertisement gives us only the 64-bit prefix. It forms the first part of our IPv6 address. The remaining part of the 128-bit IPv6 address is generated by the node. Node will create a 64-bit interface identifier using EUI-64 algorithm, which stands for Extended Unique Identifier 64. It's a method that generates an identifier based on a MAC address. MAC address is 48 bits. It will then split it in half and add FFFE in the middle, making it 64-bit. Lastly, it will invert the 7th bit of the address. Here we go. That's the 64-bit interface identifier. This identifier is then combined with the prefix to create the address. If we look at our interface, its address is exactly the same. Of course, once the address is created, the device will send a neighbor solicitation to make sure nobody is using this address. Once a unique address is confirmed, the device can start communicating with other devices on the network using its new IPv6 address. You understand why this method is called Stateless Address Auto-Configuration? Stateless, because the router does not keep track of which addresses are assigned. Moreover, this method does not require a DHCP server to manage the addresses. Usually, if you need more control on the addresses assignment or want to reserve specific IP for a specific host, then you use DHCP. If you don't require such control but only care that it works, you use stateless auto-configuration. Hope this video was useful and made you familiar with some basic concept of IPv6. In the next video, we'll talk about dual stack, importance of IPv6 firewall, prefix delegation, IPv6 DNS, privacy extensions, and also set up an IPv6 connection via a tunnel broker service. Please like and subscribe for more interesting Linux, networking, cloud, and DevOps content.